Hello, my name is Robert Smith and I'm with New River Community College, and today we're looking at calculating the change in entropy of a reaction. This is very much similar to Hund's rule back in thermochemistry that you were experienced last semester, where the total change in entropy of the reaction, we'll call that delta S Rxn, at standard state is equal to the sum of the delta S at standard state for the products minus the sum of the change in entropy at standard state of the reactants. So we can look at any given chemical equation and determine what the change in entropy for the reaction is. So I have three examples here that we're going to go through. And the values for entropy that we get in these examples will be taken from the appendix in the back of your book. But if you need to, you can find them online or any other resource that you can think of. So for this, we would find out what is the change in entropy for each of the species that are involved in the reaction first. So I'm just going to write them below the species themselves. Actually, I'll probably put it off to the side here. So we have methane, and its delta S, its entropy is 186.2. And the units that we're dealing with in entropy are joules per mole Kelvin. Okay, so I'm not going to bother writing the units until the end, but as a matter of good practice, you might want to keep the units in mind. For O2, we have 205.0. For carbon dioxide, we have 213.6. And for water, we have 69.9. Now, these numbers are all taken from the appendix, but please note what the state of each species is. So there is a different entropy for gaseous water or water vapor as there is for liquid water. So this is the value for liquid water. And it's very important that you keep track of what state your matter is in when you look up the entropies, because if you use the wrong state of matter, if you got gaseous water instead of liquid water in this case, then your result will be different. And that will likely cause you to choose the wrong answer in a multiple choice problem or yield the wrong answer on a short answer problem. So please, please, please make sure that you focus on not just the species, but also the state of matter. And I might note that I made a small error up here. The other thing we want to do in our equation is put the constants. So there's some coefficient, some C in front of each of those species. So we'll call that C sub I. If I were to write them back up here, C sub I. Okay. If these are running all over I. Okay. So now we just have to calculate our delta S Rxn at standard state, which means at 25 degrees Celsius. So it's going to be the sum of the products times their coefficient minus the sum of the reactants times their coefficient. We can just write that out. So the products are CO2 and H2O. So for CO2, we have 213.6 plus H2O. So there's two H2Os. So 2 times 69.9 minus the reactants. So minus methane, 186.2 minus 2 of the oxygen. So 2 times 205.0. And that's going to get us a delta S of at standard state of Rx for the reaction as, let's see, negative 242.8 joules per mole Kelvin. Let's do another one. Mercury oxide yields mercury plus oxygen. So for HGO solid, we have 72.0. For mercury liquid, we have 77.4 joules per mole Kelvin. And O2 we have from the oxygen we have from the previous reaction. We know that O2 is 205.0. So our delta S, standard state for the reaction, is going to equal the products. So 2, you're getting that 2 from over here, times 77.4, plus 1 times 205.0, minus the reactants, so 2 times HGO, so minus 2 times 72.0. And that's going to get us a change in entropy of 215.8 joules per mole Kelvin. So in our first reaction, we had entropy is going down. You can kind of take a look and say, why might that be? And we note that the number of moles of gas is decreasing. On the left-hand side of the reaction, we had 3 moles of gas. And on the right-hand side, we only have 1 mole of gas. So this simple change in phase decreases the number of spin states, or the number of microstates involved. So that decreases rather the entropy, and that's why we ended up with a negative entropy here. Conversely, the moles of gas increase. On the right-hand side, we now have 1 mole of gas versus on the left-hand side, none. And even if we didn't consider that to be an issue, we also see that solid is turning into liquid and gas. So the number of microstates are increasing, and that results in a positive change in entropy. So looking at this third option down here, we now see that we have a nitrogen gas plus 3 hydrogen gas, yields 2 ammonia gas. So we're going from 4 moles of gas, 1 plus the 3 on hydrogen, to 2 moles of gas. So you can expect that the entropy is going to decrease just from that. And let's validate that. So we have N2. It's going to have an entropy, again, taken from the back of the book, in the appendix, of 191.5 joules per mole Kelvin. H2, hydrogen, again, taken from a resource, whether it be the back of your textbook or online, however you're going to find this resource. In Chang, it's in the appendix in General Chemistry by Chang. So this is 131.0 joules per mole Kelvin. And then finally, we have ammonia, NH3, and that's in the gas form. Again, ammonia can be in a liquid form. Make sure you're picking the gas form of this species when you're doing this calculation. Just make sure that whenever it's presented to you, you're choosing the state of matter that is reflective of the problem. So if I had written this so that it yielded ammonia liquid, then we would use ammonia liquid, but we're using ammonia gas. So joules per mole Kelvin. And if we do this calculation, so our delta S standard state of the reaction is equal to 2, we're working with products, so 2 times 193.0 minus the reactants, so 1 times 191.5 minus 3 times 131.0, and that's going to get us the delta S of reaction of negative 198.5 joules per mole Kelvin. So you can use that, validate that in your own work, and you'll see that our prediction was correct, that you would decrease the entropy because you went from 4 moles of gas on this side to 2 moles of gas on the other side. And in our next video, we're going to be doing some more just straight up predicting.